All right, welcome back from spring break. Hope you guys had a good one. I apologize about getting the midterm back to you so late. We had a bit of a grading issue with that. So hopefully most problems are solved with the mid-year grading. If we double counted anything off, please let me know so I can give you the points back. I'm not in the business of, like, if you get part A wrong and then also get part B wrong. The only one that was a little bit tough was the AVL tree. So that was a single rotation that I kind of tricked you into thinking it was a double rotation. But it was a single rotation. And if you said double rotation but then tried to do some double rotation, it probably wouldn't have ended up as an AVL tree again. So if you ended up with an actual AVL tree, it means you didn't do a double rotation. So it wasn't really a double counting off thing. It was a little bit more than that. But if you think you should get points back, let me know. In general, the easy ones like, oh yeah, we just may have had a mistake, then I'll give you the points back. Otherwise, if you have like questions about why you got something wrong, I'm happy to chat. Generally, I try to like be fair about it and regrade your whole assignment and that sort of thing. So, but I'm not in the business of trying to take off more points than you deserve. So do email me if you have any questions about that. Let's see. I might have a couple more comments. Oh, I'll show you the actual breakdown of the grades on the mid-year too. Any questions on the mid-year exam at this point? No? I know it was long, and I apologize about that. I'll try to make the final a little shorter. The final is going to be the last day of class, so it's still just one class period. So I'll make it shorter, and hopefully there won't be too much stress on that front. OK, here's what we are doing today. Yes, question, Katie. The final is cumulative. Yeah, I mean, it's tough not to be in this class, to tell you the truth. But I probably won't ask you another AVL tree thing. I mean, what's the point, right? But it is cumulative otherwise. Yeah. OK. All right, so here's what we're going to do today. A couple more comments about the midterm. Then we're going to talk about a little Unix tip of the day called mail and mutt. Turns out there's a mail server on the homework server, which basically means that you can send email from there. You could also receive email there too. But you probably don't even realize you have an email address that's your username at cs.tufts.edu. If you want to use it, you can. I just have all my email forwarded to that one, and I only check that one. It's probably easier than having multiple email addresses. We'll do that. Then we'll go into this topic called sorting. So we've talked about sorting a little bit before. And in previous CS classes, you might have seen it a little here and there. But we're going to kind of delve deep into lots of different types of sorting. OK? There's a bunch up here. We'll talk about some other ones later. Today, the next 2 days is going to be on sorting. And in fact, your next assignment, which is already out, is actually, I guess I technically put it out like Saturday. And that is, or maybe Friday. And that is on sorting. It's actually, I think it's an interesting assignment in the sense that you get some more creativity in what you can do for the assignment. You actually have to write 3 sorting algorithms. One you have to do that's a particular one, and the other 2 are kind of up to you on which ones you want to do. So, and the third one, the final one, you can do pretty much any sort you want that's not like a crazy weird sort. We'll talk about those ones in a little bit too. OK? Any questions before we get going on that? All right, the mid-year exam, let me see. Hopefully, there it is. This was the grade breakdown. It's not a bell curve, which is fine. I actually like it when more people do better than worse. The average was 85 out of 84.5, 85. Pretty good for that test. Again, I know it was pretty long, but most of you did pretty well. If you're below about here, you probably want to talk to me about what happened on the test, and we'll try to figure out a way to get a little better for the next exam. OK? Anybody else have any questions on that? Any particular questions about the mid-year? No? Yeah, I think I like publishing the key, because then you guys can look at exactly what we thought you should write down. So that's that. OK. A couple people did get some bonuses and do well, so more than like 60 points. A couple people. All right. OK, enough about that. So Unix tip of the day. So there is, as I said, there is a, let's see, there is a mail server on the homework server. And how you use it is you actually just type mail-s and then the subject name in quotes and then an email address, and then you just type it, start typing. Anybody ever get an email from Bruce Millay? You know how they're always like super duper text mode, like that's it, like just text, and like he's got little like ASCII art and stuff in there and whatever. It's because he uses like mail as his main client. Like he like just types it in the command line. Like that's how he uses mail. So this is definitely old school. Okay, but here's what we do. So let me do this. Mail-s. So oops, where'd it go? There it is. Mail-s, and the subject will be sorting. And the email, who should we send this to? Let's send it at to, I did this one earlier, prez@whitehouse.gov. All right, maybe he'll get it, right? Dear Mr. President, I hope you're having a nice day. What do you know about sorting? Thanks. Comp 15. P.S. Say hello to Michelle for us and ask her about sorting. I don't know. Whoops. OK. Anyway, and then you hit Control D, and then it blasts off. And now it's gone, right? And I actually did this earlier. I didn't get a return email, so somebody's getting it there. I don't know. So that's how you can send an email, and boom, it's just straight up, there it is. And it will actually come from your tufts.cs.edu email address, or rather the other way around, cs.tufts.edu email address. So you better, if you want to reply, you have to check like you've added email address, which you can do online. There's a webmail client if you want to do that. OK, and then that's one way to do it. But what if you wanted to send the president an email or an actual attachment? You can do that too. You have to use a slightly different email client, though. It's called Mutt. I don't know, it's something to do with dogs or something. But and let's see if we can do this. Let's see. Oop, there we go. Mutt. Let's see. Before we do that, let's see what we can send him. You want to send him our lab 6? Sure. All right. So let's see. Mutt and lab6.zip. And let's see. So you have to have a -a for attachment. Let's see. Barack at whitehouse.gov. And the subject will be tries. I think that was what Lab 6 was about. And then this one actually brings up a little screen, and you actually finish the email by putting a period by itself on a line. A little weird way of doing it. Hey, again, hope you enjoy this lab. Thanks. Comp 15. And then you put a period, and it blasts off. And there you go. So now you've got we've sent the lab6.zip to the president. And maybe he'll reply to us. So that's nice. Or maybe the FBI will come knocking at my door. I don't know. We'll see. So anyway, so that's how you send emails. Any questions on that? If you want to do it from the command line, you can do it. It's a good way to send, let's say, your comp11 zipped up file that you made last week to yourself, or any other kind of attachment, et cetera. All right. OK. So let's go back here. So that's enough about the Unix of the day. Now, sorting. Let's see what the president knows about sorting first. We asked him what he knows about sorting. Has anybody ever seen this? You probably know, if you know what I'm talking about, you might have seen this. So that is actually Senator Obama, and he's at Google. You can tell Google font. This, by the way, this is a good reason to make, if you ever have a company, make your logo really distinctive. Because all we need to see is like GO, and we know you're at Google, right? It's easy to see. He went there, and he had, this was like pre-becoming president, and they did a little interview with him about being what he wants to do president. Let me see if the sound is high enough on this. Let's see. Nope.
I like to think of the presidency as a job interview. Now, it's hard to get a job as president, and you're going to the interview. Now, it's also hard to get a job at Google. We have questions, and we ask our candidates questions, and this one is from Larry Schwimmer. What, you guys think I'm kidding? It's right here. What is the most efficient way to sort 1,032,000 integers?
Well,
Maybe, I'm sorry, maybe.
no. I think
that's not a,
I think the bubble sort would be the wrong way to go.
Come on, who told him this? Okay. I didn't see computer science.
We've got our spies in there.
Okay.
Okay, so the president is telling you right now that one type of sort that you don't want to do is a bubble sort. Anybody heard of a bubble sort before? Probably programmed it maybe in some other class or whatever. I hear that some people like actually learn it at Tufts, which is terrible to me. Bubble sorts are a terrible way of sorting, and we'll talk about why sometime later. I'm not even going to teach it to you. If you want to actually go look it up, you can go find out. But I listen to the president, and he says no bubble sort, so we're not going to do the bubble sort. We are going to do lots of other types of sorts. Okay? Anybody? What other types of sorts are out there? I flashed a list up earlier, but what do you think? Yeah. Heap sort. Yeah, we talked about that. You're going to do a little kind of a heap sort tonight for lab, or tomorrow night for lab. What are the ones we have? Yeah, sir. Merge sort. Yeah, merge sort's an interesting one where you actually take two lists and you kind of two sorted lists or partially sorted lists and merge them together. Okay, and you actually have to do that. So that's a different type. Yeah. What other ones? We've actually talked about one in here already. Any idea? Yeah. Insertion. Yeah, it's insertion sort is the one. And that one is a pretty easy one. And it also has some good uses, although it's not a very good one in kind of the big picture. Anybody else have other ones they've heard of or used? Yeah. Selection sort. We'll talk about that one too. Another pretty terrible one, but it is better than bubble sort. Yes, other ones. Anyone ever heard of quick sort? No nods. Oh, good. OK. Quick sort is that's fine. Quick sort is one. We'll actually learn that on Wednesday. Quick sort is really what I consider the first real algorithm we learn in this class. Now, I know we've done algorithms like we know bubble up and bubble down, and we've done some more algorithms. But quick sort is one where you go, oh, I see. This is an algorithm for computer science. Like this is it. That's the kind of the bottom line. So you'll see that. OK, so there's lots of different ones out there. In fact, I'm going to show you another little video in a minute about other types of sorts. We've talked about sorted lists, right? Remember the sorted priority queue? That was an insertion sort, where we actually put things into the list and kept it sorted as we were inserting it. And that was an insertion sort, the way we did it. But sorting in general is this idea of, it's not very monumental, but it's this idea of saying, taking a bunch of elements and putting them in order, right? And most often, the order is numerical. In other words, lowest to highest or highest to lowest, or lexicographical, meaning alphabetical. And there's some slight differences about lexicographical order. So we'll get to that actually again on Wednesday. We'll see why there's a difference there and why we care. But if you have words that you're putting in order, putting them in order by their actual alphabetical ordering is the way we generally do it. OK, so that's sorting and kind of what we do. In order to sort some elements, OK, in order to sort some list, there's a couple things that have to be true. OK, first of all, it has to be in a non-decreasing order. What's another word for non-decreasing? You would think it's increasing, right? But it's not actually increasing, because non-decreasing takes into account ties. OK, so when things are ties, they are not necessarily increasing, but they are certainly non-decreasing. Right? 3, 4, 4, 4, 4, 5. All those 4s are non-decreasing. So it's a technical thing, but that's the way we talk about it. And this would be if you are going from smallest to largest. Okay? And the other one is you have to be a permutation of the input. In other words, and this is also not exactly rocket science. In other words, you have the list, and if you've sorted it, you can't end up with any more or less elements. They have to be the same number of elements and the same ones you started with as a permutation of the input. OK? All right, so sorting is actually pretty well researched. Like it's been going, people have been thinking about sorting things for millennia. But although there aren't too many new algorithms coming up, in 2002 there was this algorithm called Tim sort that a guy invented. Any idea what his name was? Tim. His name was Tim, indeed. He came up with this 2002, so that's recent history. And what he did was he was playing around with sorting and came up with this sort and said, hey, this is actually a pretty good sort. Word got around that he had created this, and then the makers of the Python language decided to start using it. So now when you type sort in Python, you end up using Tim's sort. And I think also in Java these days as well. So it's actually pretty good. That's kind of neat. Interestingly, about a month ago, I read a little post that said that somebody had found a bug in Tim's sort. So it turns out they've been using it for like close to 15 years, and somebody found a bug in it. Nobody ever noticed before, but it's there. So they had to fix that too. So that's just like really current stuff. So while sorting, in some sense, you're like, it's boring. I'm just moving a bunch of numbers back and forth. It's actually still being researched, and people are still doing things with it. So kind of neat in that sense. Comparison sorts. Here's a bit of a spoiler alert. For comparison sorts, in other words, sorts where you have numbers that you are comparing, this one's smaller than this one, or this one's greater than this one, when you're comparing them, fundamentally, you can't do better than order n log n. OK? And that's as good as you're going to do. OK? Hey, Katie, you're in Comp 160 now, right? Have you talked about sorting already?
Yeah.
And did you guys get into the details of why n log n is the best you can do? Yeah. So when you take 160, you'll dig into those details. For now, all you really need to know is, hey, the best you're going to do is n log n. OK? And so that's pretty good. It's not amazing, but it's pretty good, right? But it's kind of what we're hoping to get, n log n behavior. OK? We will see some sorts that do better than n log n, but they're not comparison sorts. Then you say, well, what does that mean, not comparison sorts? You will find out, OK, in a couple days. All right? The other thing we need to consider is not only the time complexity, n log n being as good as we can do, we also have to consider the space complexity. Okay? In other words, and we haven't really talked about this in any other situations, the space complexity means here's your array of numbers. Do we need to make another array to temporarily store things in while we're doing that sorting? Or can we do the numbers by just shifting in that one array? Okay? By saying something is done in place, we're saying, OK, we don't need to create another set of like array space for our list. You're just going to do it right in place in the one array. And some sorts do that, some sorts don't, and we care about that. OK? It's an important factor when choosing a sorting algorithm sometimes, especially when you're talking about like big sets of data and a small amount of memory. Okay, let's say has anybody ever done any Arduino programming or iPhone programming or anything like that? Yeah, it's important to think about the amount of memory you're taking up, because those are just memory-limited devices in general. And so if you only have 32 kilobytes of memory in your Arduino or whatever, and you're going to try to sort 30 kilobytes of data, you can't choose a sort that's not in place, even if it happens to be a faster sort, because you're just going to run out of space. So that's a concern. OK? All right, so those are some kind of basic ideas of sorting. In-place sorting can also be what we call stable or unstable. Let me give you an example. So let's say we had some numbers. Let's say we had 4, 3, 4, 8. OK? Somebody sort those individual digits for me. 3, 4, 4, 8. OK? Which 4 is this one? It doesn't really matter, does it? If you're just sorting numbers, a 4 is a 4 is a 4, right? But what if we labeled these A and B, right? Which 4 is this one now? Well, who knows, right? We haven't figured that out, but it could be A and B like that, or it could be 3, 4, 4, 8, and this one could be B, and this one could be A. In the process of sorting these, the one that started out in position 0 might end up in position 1 or position 2. OK, so that's the difference between a stable and an unstable sort. A stable sort keeps the ties in the same order they started in. An unstable sort might switch them. It doesn't have to, but it might switch them. OK, that's the difference. Sometimes we care about stability in our sorts. Like with just numbers, nobody cares, right? A number's a number's a number, and it doesn't really matter. But what if these had like associated, these were keys for some other information? I don't know if you've ever done any sorting in Microsoft Excel. But if you sort in Microsoft Excel, let's say you've got a list of all these things, and you've got names on one column, and then, I don't know, other numbers and things in other columns. If you first sort by like last name, and then you go and sort by one of the other columns, right? It will end up sorted such that the columns are like the sort is now by that second thing that you sorted, but the names for ties are still in alphabetical order. Okay, that's a stable sort, and sometimes you want that if you want the ties to remain in the same order. Okay, and sometimes you don't care about it, but we do care about this in some cases. Okay, that's what an unstable versus stable sort is. Okay, as I said, we're going to do this on today and on Wednesday. There are lots of different places online you can look up sorting. It's like all over the web, and people have come up with some really clever types of ways of visualizing this. This one's actually one of my favorites. This is a picture of a bunch of sorts. We talked about most of these. Okay, insertion, selection, bubble, shell, merge, heap. We didn't talk about shell. Quick sort, and then there's this quick 3 over here. And then what it's doing is it's showing you on the kind of the y-axis here, it shows you if the numbers started out randomly, if they started out almost sorted or nearly sorted, in other words, only a few of them are out of order, or if it was completely reversed, or if, this was an interesting one, if there's a few unique ones in here. In other words, you can kind of tell from this what it is the length of the bar is how big the number is. Let me see if I can make this a little bigger. There we go. The length of the bar is what number it is. Notice that many of the lengths are the same, and then many of the other lengths are the same. There's only a few unique numbers in that list, but they're still out of order. Okay? And what you can do, this is the neatest part, you can actually click on these buttons up here and then see all the sorts happen in real time. Right? And notice most of them are done right now. Poor old selection and bubble sort take forever. Right? But you can now see everybody's sorted, and you can kind of now see, hey, this is the same, very few different ones here. But you can also check, let's just check how, this insertion thing works. We can just do the insertion ones, and it'll do that. And it'll show you some things there, right? Which one's taking forever in insertion sort? Reversed, right? And we'll talk about why that's the case in a few minutes, right? Let's look at quick sort. You would hope it would be quick, because that's what its name is. Take a look at this one. Right. We're done. Well, we're not quite done. Right? Some of the things took a while down there. In fact, if you just look at the few unique ones, quick sort actually doesn't do so well. Lots of other things are done before quick sort gets close there. And there's a very good reason for why that's the case, which we'll talk about on Wednesday. Selection sort was still really slow. But that's it. Bubble sort, again, terrible sort. Similar to selection sort in its behavior, but even worse. In fact, I'll put a Piazza post up about why it's so terrible and why the president doesn't like it either. So this is a good way of looking at this. This also gives a lot of the algorithms, gives lots of information. So good reference if you want to go back and look at some of these sorting things. Okay, that's that one. Here's what I'll do. I will show you this next little thing. Well, there's also another one. There's another comparison one, or another visualization one, which is neat. This one goes a little slower. Let me bring this up a little bit. This one goes a little, well, can go whatever speed you want. But it shows you in order. So let's look at, I don't know, merge sort, which we'll do later in the week. So that's not a good example because it's not showing it. We'll do insertion sort. Okay, so insertion sort, you'll see what happens here. It's going to go and kind of make some changes here. And if you don't get what's going on here, that's fine. We haven't really talked about it yet. But like I said, this is a very good way of visualizing this. If you can't remember what some of these sorts are, if you want to get your brain wrapped around it, then go to this one. Some of the ones let's re-randomize this. Let's pause. Oops. Let's do this. Let's randomize the array, and then I'll do quick sort kind of fast for you just to see what's going on. And notice this line here. That's important. Right? Okay. And then it does some other things, and you'll see when we actually learn this, you'll see what's going on here. But it's kind of neat. This, however, is not the neatest way of looking at this. Neatest way is, where did it go here? Well, probably the second neatest way. Hang on. Let me show you. Here it is. YouTube on 15 sorts in 6 minutes. And I think we can spend 6 minutes looking at these. This one is, OK, hold on. Ooh, it's going to be really loud. Hang on. It's kind of loud. So they put music to this, actually. Well, music's probably not the right word. They put sounds to this. And what this is it's a bunch of sorting, different sorts. I'll blow this up so you can read what these are. But it's different sorts, and they kind of show you how it sorts in real time. And it's pretty neat. The width of the bars tells you how many they were sorting at one time. So if you have really thick bars, it means it's probably a terrible sort, because they didn't want to sort too many in this 5-minute video. OK? All right, so let's blow this up. And there we go. This is selection sort. They always do that. They always end with the little whoop thing. You can tell that the lower numbers are down here, and those are a lower frequency for the tone they give, and the higher numbers are a higher frequency. And every time it touches one of those numbers, it blasts out the sound associated with that number. That's how it's working. And notice, not so many bars here. Selection sort is terrible. This is insertion sort. Not so great at the end. There we go. The next one is quick sort. See if you can figure this one out. It's pretty cool. This is a recursive algorithm. Notice really tiny lines. It's fast. OK, that was quick sort. This is merge sort. This one's neat looking too, because you can tell kind of what's going on. There we go. All right, let's see what the next one's heap sort. First of all, it heapifies it. Notice something. It's figuring it out backwards. All right. Next one is radix sort. This is a fun one. If you can figure this one out, you're a better person than me on this one. Fast. It's a great sort. This is also radix sort, done in a slightly different order, as it turns out. OK, this is the sort you'd get if you were just using the standard library sort. Notice how jagged it is up here? That's a specific reason for that, being really jagged. It fixes that at the end. Now it's fixing all those jaggedy things. And there's a good reason for why it's doing that. It's an interesting reason anyway. OK. This is a stable sort. The other one was not stable. This one's a stable sort. You can kind of tell what kind of sort it is. Anybody? Merge sort. It's a merge sort, which is a stable sort. All right, what else do we have? Shell sort. This is a really interesting one that we'll talk about today. Notice those like gaps there. One more pass, I think. Yeah. Okay, that's an interesting one, shell sort. Here's your bubble sort. Notice how wide the bars are, because it's terrible. This one's fun. It's a cocktail shaker. All right? I don't know why it's called the gnome sort, as in the garden gnome, but maybe it looks like a gnome's hat or something. I don't know. All right, let's see. Bitonic sort. Kind of looks like merge sort, but then it gets wacky. This is a good one if you're doing parallel sorting. In other words, multiple computers sorting the same data. Yeah, it's a weird one. This one's called Bago Sort. Anybody ever heard of that? Yeah, so I'll tell you about Bago Sort in a second. This is the last one, and let's just say that there's like 3 more minutes of it, or another like whatever. And here's how Bago Sort works. Bago Sort is the following. Let's say you have a deck of cards that you want to sort, right? You look through it and you say, is it sorted? And if not, you shuffle it, and then you look through it and say, is it sorted? And then you shuffle it again, and then you look through and say, is it sorted, right? Best case asymptotic complexity on that? What is the best case? 1, right? It's already sorted. Worst case? Things like the heat death of the universe and things come into play, right? Yeah.
Any random sort is a Bago sort?
Any random sort. Well, if you're trying to actually sort it, then that's, yeah, you can do that. The 52 card pickup type sort is the way I like to call it. Yeah, Bago Sort's an interesting one. There's actually one called the quantum Bago Sort, which for you physicists out there, it's basically you check if it's sorted, and then you destroy all the universes in which it's not sorted in. And that's constant sort. It's actually pretty good. Your job is to figure out how to destroy all the other universes where it's not sorted, but that's for you to figure out. The other speaking about decks of cards, right? Who's taking Comp 61 or has the discrete math? Yeah. So you might have talked a little bit about probability and things in there. Turns out with a deck of 52 cards, if you shuffle a deck of 52 cards and then look at the order, the odds are like 99.999999999% that you will have a new ordering of a deck that has never ever been seen before. All right? If you shuffle it and then look through it, that order has never been seen before with almost 100% probability. Because 52 cards, a permutation of 52 cards, is such a huge number that it's very unlikely that anyone else in the world who's ever shuffled the cards will have a same deck. So, interesting. One other reason why this is probably not a good way of sorting. And you're not allowed to do this one for your homework assignment. OK, so maybe we'll go back to some of these a little bit later when we figure out some more of these sorts. OK? But those good ways of visualizing it. OK, let's talk about some specifics. We've looked at insertion sort before. OK, we've looked at keeping the values in an array. This time we're going to do it where we're not adding to an array. We've got an array that's unsorted, and we're going to use this insertion sort to make it sorted. OK? And we will do this in place. Okay? In other words, we're not going to have any extra space requirement, except maybe a temporary one to hold the one we're working on. Otherwise, that's it. Here's how it works. Iterate through the list, starting with the second element. Remember when we were defining the maximum of an array? Why did we start at the second element? I remember. What do you think, Lenora?
The way you would compare it is to compare like I to I minus 1 instead of I to I plus 1, because if you did I plus 1, you would go over
Yep.
the array.
Yeah, you're comparing. There's no point in comparing 9 to itself or anything else. There's nothing else to really compare it to. So you might as well start with 5 and do the comparison of 5 to 9. OK, so that's what you do. So you iterate through the list, starting with the second element. At each element, I wrote it like this. You don't have to necessarily shuffle it. It's like shuffling them up. But basically, at every element, shuffle the neighbors up until the proper place is found for the element. So in other words, if we're looking at 5, you keep going backwards from 5 until you find one that 5 is greater than. And you know that it has to go right before that one. OK, in other words, you go from 5, you go to 9. 5 is less than 9, and there's nowhere else to go. So it's got to go before there. OK, so it looks kind of like this. OK, 5 is going to be there. 9 shuffles up 1 and ends up there. OK, 10, you compare 10 to 9. And 10 is already bigger than 9, so there's no reason to move anything. How do you know that 10 can't fall somewhere down here? Because it's already sorted. Everything before this is already sorted. OK, so that's not a bad way of doing it. OK, then you hit 8. Well, 8 is less than 10 and less than 9. So both 10 and 9 have to shuffle this way, and 8 goes there. And you know to put 8 here because it's greater than the 5. OK, so you check against 10. Nope, it's got to be farther to the left. Check against 9, farther to the left. Oops, 5, it's got to be right on this side of 5. OK, pretty straightforward, right, like that. So 10 and 9 shuffle up. Really what you would do, you wouldn't go from this side up. You'd basically put 10 here, 9 here, etc., and then do it that way, right? It's a loop backwards. Yeah, Alex. Yeah, you probably need to store the 8 in a temporary variable. Yeah, it's not a bad idea. Putting it just in a temporary and then shuffle up, and then you go. You could, if you really wanted to, you could, well, even swapping, you're going to have a temporary. You're probably going to have a temporary. But basically, you could say 8 goes here, 10 goes here, 8 goes here, 9 goes here. But either way, you're going to have one extra temporary. Yeah. Yeah.
You could do it with just like adding the numbers together, then you don't need a temporary.
You could add the numbers together.
Like if you want to switch 10 and 8, add them together and subtract element 3 from element 2, you get 10 in the 8th place instead. And then
What do you do with the 8? How do you know the 8? How do you get back the 8?
I mean, I think that would swap it, I think.
Oh, OK. I guess I didn't think about that. But you're still need to keep this in some other variable, probably. But it's an interesting idea. Yeah. OK, so that's really the whole algorithm, right? Just shuffle them up. So now when the 8 goes there, look at the 12. Nope, it's already bigger than 10, so nothing needs to be done, which is great. We know that sometimes this is going to work great. 11 only needs to swap once. 14 doesn't need to swap. Then we get to 2. 2 is a pain, right? Because 2, you go, all right, 14, 12, 11, 10, 9, 8, 5. Oh, they all have to move, right? Boom, 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 boom. And you got to move them all up. So that's a pain when you get like the smaller numbers at the top. And everybody shuffles up. OK? And then 22 and 43 are fine. All right. Complexity. Let's talk about the complexity of this. OK? In fact, do this. Talk to your neighbor about this. Say, hey, worst case complexity of this is this. Best case is this. And then figure out if you can come up with examples for both those cases. How many different sorts did you do in?
Like actually analyze?
Yeah.
We did sort, sort,
In depth, OK. And you got into like how many extra like better than, or how much, like n log n. You went into all the details of that, right? OK, good. Yeah, we're not going to do that in here. I'm sorry. Good. OK, who thinks they know the worst case complexity of this? Yeah. Why is it n squared, Sarah? Yeah, if it's reversed, and I like that. If it's reversed, right? Let's look at an example of reversed here. Let's say it was 7, 3, 2, 0. Nope, that's not reversed. Oh, sorry, it's reversed for going up, whether we're going from 0 to the other way. First, you do this one. Does that need to go anywhere? No. You're going to check this one. Does this one need to change? Yeah, you need to. 3 and the 7 need to swap, right? Then you look at 2, and then you check here, and you go, oh, they all have to swap. So 7 goes here, 3 goes here, 2 goes here. And then the 0, same thing. Boom, boom, boom. Everybody has to move, right? So then you've got 7 and 3 and 2 and 0. And yeah, basically n squared number of times. For every element, you have to go through the rest of the elements you haven't sorted yet, at least, right? Okay, so you could have to go all the way back down to all the way back down to the beginning again, right? And you can see that pretty well on the, let's see, where was it? Here it is. So selection sort. Oops, actually, here's what I'll do. We'll check selection sort, and for nearly sorted ones, you can see it's, let's see, it's actually kind of slow here. Thought it was faster. Oh, thank you. I clicked on selection sort. Thank you. Insertion sort. Here we go. There we go. Nearly sorted insertion. Hang on. Back. There we go. Nearly sorted there. There we go. There we go. Nearly sorted gets done really quickly. Okay. Reversed, though, yes, you have to go through the whole thing each time, right? So it's going to go back, 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 back. And this is where it takes up the time. Okay. All right. So very good. What's the best case asymptotic complexity? Yes. Okay. So it gets to the next one here, and then it has to go all the way back down. And then it gets to the next one, and it has to go all the way back down. And it gets to the next one, it has to go all the way back down, right? So yes, there's a bit of the edge cases here where it only has to go halfway or a quarter way, whatever. But each time it has to do that. So in the end, it ends up being n squared. Yeah, in the overall. Okay, it's almost done. There you go. So that was the reverse. What's the best case complexity? Yeah. Is it n? Why would it be n? Yeah, you do have to at least go through the list once, right? And you have to check each one against its previous one. But if it's in what order is it going to be to make it n? Exactly n. What order do they start out in? Already sorted. Yeah, already sorted. If they're already sorted, then you don't need to actually do any changes. So you just have to walk through them. Okay? Worst and best. Perfect. OK, that was insertion sort. OK, the average performance is actually n squared, OK, which is not good. We don't like n squared behavior. Remember, that's a quadratic behavior, and it's not very good. So we don't like that. But if you have very small arrays, it's actually not so bad. Because if you have an array of like 10, what do I mean by small? Like 10 or 15 maybe. Because doing 10 squared is only 100 operations, and that's nothing. Remember the sort where it was like jaggedy, and I pointed out why it was jaggedy, and it fixed it all at the end? That was because it was doing basically a quick sort, but skipping all the ones that were small, because it just handled them later with insertion sort. So it was like a hybrid type of sorting, where it goes and it says, you know what? Insertion sort's pretty good for when it's a small number and you don't have lots of overhead. So if we have very small arrays, insertion sort's pretty good to do. Okay? And then space complexity, we don't actually have to move anything. Everything was in place, so we might have one for swapping, but that's it. Otherwise, in place. So pretty good in that sense. Okay? All right. Selection sort. OK. Selection sort is another in-place one. Here's the algorithm for selection sort. Find the smallest item and exchange it with the leftmost unsorted element. This is the part that we're going to be kind of concerned about. How do you find the smallest element in a list? Yeah, if it's not sorted, you have to go through the whole thing, right? And then you repeat the process. So if you look at the animation here, see the actual animation. If you look at the animation for selection sort, OK, look what it's doing. Starts out and it says 13's the lowest, 12's now the lowest, 9's now the lowest, 5, oh, okay, 5. Now 13's still lowest, okay, back, 12 is now the lowest, 3, okay. So, and then goes through all the rest. You see how it takes so long? It's pretty terrible, right? What's the worst case complexity of this one? Also n squared. In fact, an even worse n squared, because it has to like literally go through every single one every time. OK, what's the best case scenario? Oh, it's also n squared, right? Because you're going through all of them. There's no way of like gaining anything out of this. This is a particularly terrible one. It's not quite as bad as bubble sort, but it's pretty bad, right? The idea is just go through the entire list, find the smallest item. So the first one, we find the 2, and then swap it with the next one. Then you find the 5. All right, well, it can swap with itself. Doesn't need to swap with anybody. Then you go through, and the next thing you find is the 9. I'm sorry, the 8, and then you swap it with the 10, and then you find the 9, and that gets swapped with what is now the 10, et cetera, et cetera. OK? So it keeps going on. I'm not going to do the whole thing for you, but it's slow and kind of painful. Very easy to code. It's like 2 for loops, right? Boom. But that's it. Okay? And worst case, oh, n squared. Best case, n squared. Average case, n squared. Blah. We don't like that. Worst case, it's OK, so it's in place. But there's, there's better solutions than this. Now, there is one case where you might want to use a selection sort over some other sorting. OK? I gave this to the earlier class, and nobody figured it out. So I'm going to give you a hint. OK? And the hint is going to be the Boston Marathon. Now, talk to your neighbor and try to figure out why selection sort is actually a pretty good sort. Talk to your neighbor about it before. Or do you have a question about it?
No, I think
Talk to your neighbor about
I
it.
might have mentioned it in an earlier class.
Oh, I might have mentioned it in earlier class. Did I?
I think so.
Oh, I did? Darn. All right, what is it? What was it?
You only need the first 5.
You only need the first couple, right? In the Boston Marathon, the first few people are the ones who get trophies. And if you've got 10, 20, or 30,000 names to go through, just go through, find the first one, go through, find the second one, go through, find the third one. Don't do a sort that the last thing you do might be the end result, like might be the first person, right? You just don't know for some of these other sorting methods, right? Which one? Insertion sort, you could have to wait to the last one before you get to that's the top one, and you don't get there until it's almost all the way sorted. Okay? With selection sort, boom, you're just ready to go. Okay? I forgot that I mentioned that before. Oh well. Anyway, that's that. Okay, you'll have to code this one for the homework, but that's only to kind of give you a good baseline for some of the other ones. Okay, heap sorts. So we talked a little bit about heap sort the other day. You're going to do kind of a version of heap sort in tonight's and tomorrow's lab. Heap sort works the following way. You are going to first heapify the array. In other words, it's going to be completely out of order. And then you're going to heapify it. Okay? Then you're going to go over the array and perform remove min on it. But instead of returning the minimum elements, we're not going to return them because we want to keep them. Guess what? We already have an array because our heap is in an array to begin with. What we're going to do is just keep the one we removed at the end of the heap in the array and just say that the array size is 1 less so that we don't consider that as part of the heap. Okay? So we're going to do that. And when the iteration is complete, you're going to have the array sorted from low to high priority. So in some cases, it's going to be backwards depending on your priority. But it's going to be in the correct order, which is kind of nice. Okay? Remember when the heap sort, it went from like top down like this? That's kind of why, because you've got this, you're keeping the last one in like the final position. Okay? So let's actually look at this again. This will actually be a good review on how to actually heapify something. Let's say we have a heap. Let's do this. Yeah. There we go. Like that. We'll say that it's, I don't know, 14, 2, 3, 1, and 7. And let's heapify this. Let's see. I almost did it already, but there's not that many to do. How do we heapify something? Do you guys remember what the algorithm was for it? This is not in any heap order, but how do we do it? Just to heapify it. you do bubble down, but you got to know where to start. This is going to be a for loop, right? It's going to be a for loop going from the first one that what? That has children, right? So this one doesn't have children, this one doesn't have children, this one doesn't have children. Turns out this is the first one going backwards that has children. You're going to down heap this one. So down heaping this one, it replaces it with the smaller of the two children. This is going to be a good review for tonight's lab too, right? 2 and 1. OK, and we're done with that one. And then we go up to here and we down heap this one. So where does it go? It also gets replaced by the 1. And the 1 goes up there like that. And then 14 is here. But we're not done quite yet. We still down heap this one. So it does what? Gets replaced with a 2. So 14 and 2. Do we have a proper heap now? Yeah, we do. We have a min heap, right? Like that. In our array, it would look like this. Right? It would look like 1, 2, 7, 14, and 3. OK? And here's, did I screw something? Oops, I forgot. I have this end space. Yeah, that end space is the one we care about. The other one we don't really care about. But yeah. OK, so if we're going to now sort this, because that obviously is not sorted, but if we're going to sort this, it's pretty easy to do, right? We just say, fine, we're going to remove min, which in this case is the 1. And where are we going to put it? Well, let's put it where it actually is, like outside in the array still, but not in the heap anymore. So we're going to take 1, and we're going to swap it with the 3. 1 and 3. This is no longer part of our heap. OK? And we have to then down heap the 1, because that's the algorithm. It turns out it's sorry, I'm not doing it. We have to down heap the 3. 3 and 1. And we have to down heap the 3. So that's going to switch 3 and 2. And then we have looks like this. And we do the same thing again. We take the 2 and remove min. We just call remove min on it. And it's a little different because we have to store it here. But we remove it, meaning we put it here. And then 2 and 14, like that. And now these are not part of our heap anymore. Down heap 14, let's see, it's going to be here. So 3 and 14, like that. OK. Next, we'd remove 3, switch 3 with the one that's now part of the last one in our heap still, 3 and 7. All right, and so 3 and 7, and we down heap 7. And this is now no longer part of our heap. Down heap 7, it's already down heaped. Remove 7 and 14, or remove 7. So that's going to be there. And then 7, and then 14. That's no longer part of our heap. So 14, and then we're done, because that's the end of it. 14, 7, 3, 2, 1, and it's just reversed, but it's in order. OK, so that's how heap sort works. OK, it's pretty fast, actually. Heap sort is pretty darn fast. Here's how it looks in this case. First, you heapify it. Then you actually call remove min and swap them. Now 2 is not part of the heap anymore, but it's part of the array. Same thing. Let's see. Now 5 and 22 need to swap, and we down heap a bit. And then 8 and 43 swap, et cetera, right? 9 and 14 swap. And I think that's about it. Yeah, et cetera, et cetera. OK? So that's how it works. And the asymptotic complexity is pretty good, actually. OK? It's n log n to do this, which is great, because that's actually the best you're going to do in the asymptotic sense. So it's actually a pretty good way of doing sorting. OK? It's nice and fast. Best case, worst case, average case, all n log n. OK? It is no longer a min heap, although somebody earlier today pointed out that it's a max heap, which is kind of nice. But it's no longer a min heap. So you do break the heap property if you're going to do this to make it this like a min heap. But the space complexity is in place, perfectly in place. OK? You might have an extra temporary one, but that's about it. OK? Heap sort. All right. The next one we're going to talk about is kind of a fun one. This one's called shell sort. You ever play the little shell game? Like where you have like a ball underneath the shells and you do it around like that? This has nothing to do with that. I actually used to think it did, but it's named after this guy named Donald Shell. This is a generalization of insertion sort. So remember, we did insertion sort. When was insertion sort particularly good? When it's mostly sorted, or actually perfectly sorted, but mostly sorted. Turns out that because of that, this takes advantage of that and says, well, maybe we can get a list of numbers into a situation where insertion sort will work pretty well. Well, Donald Shell's idea was to keep doing insertion sort, but not in the normal way where you have to move things all the way back through all the way back. He said, well, let's do it a little bit differently. He said, let's do this. And by the way, this is not so hard to code because it's just insertion sort. It is a little tricky because you have to figure the loop ends out properly, and it's a little tricky, but not impossible. Basically, you rearrange the elements such that every hth element, that's a terrible thing to say, hth element, produces a sorted list which is said to be h-sorted. Now, what does that mean? That means that if we have numbers like this, 14, 7, 3, 2, 1, if we're doing 3 sorting, that means that like the 14 and then the 2, which are 3 apart from each other, right, 1, 2, 3, are going to, after we do this, those 2 will be sorted relative to each other. We don't care about anything else in that case, but then this one, the 7, and the 1 will be then sorted relative to each other, and the 3 is just going to be sorted relative to itself as well. Okay? So that would be, once you do that, then you would say that this is now 3 sorted in that case. Okay? So we do that first, and what that does is that takes this kind of random set of numbers, and it partially sorts it. And then the next time through, insertion sort works a little better because it's already partially sorted. And then the next time through, insertion sort works better because it's partially sorted. So first you do this. You rearrange the hth elements. Then you repeat with what we call a smaller gap. In other words, k is now going to be less than h. So first you're doing 5 sorting. Then you do 3 sorting after that. If you do that gap sorting like we were talking about, it doesn't break the previous sort that you did. Right? So it just makes it better. It makes it go from partially sorted but not so great to even better partially sorted. Right? And then you do a smaller gap size, and it makes it even better partially sorted. And every time it makes it better partially sorted, insertion sort works better. So it's like it gains on itself in that sense. And you continue this process until you reach a gap size of 1. And when you get to the gap size of 1, everybody's perfectly sorted. Okay? So that's how it works. Now, I'll show you an example, and then we'll talk about it a little bit more. Okay? Here's the example. So I've tried to color code this so that you can kind of figure out what's going on. But at the top here, we're going to use the gap sequences of 5, 3, and 1. Now, if you choose to do this for your homework assignment, you can choose shell sort. A lot of people do. I would do many more than just 5, 3, and 1. Right? I'll show you some gaps, the gaps that people have come up with over time. And you don't want to just pick a few. You want to pick like a proportion of the total number of elements that you have. I'll show you that in a minute. But basically, right now we're going to practice this on a gap sequences of 5, then 3, then 1. And you always have to end up with 1, because that's going to catch any stragglers at the end. So this is what we have. We have our array, 62, 83, totally out of order. It doesn't have to have started at 1. I used the thing from the heap sort. But it's just out of order. Okay? And what you do is, for the 5 sort, first you sort 1 versus 6 versus 11. Right? So 62 versus 6 versus 11. Those 3, the red ones here, have to be sorted relative to each other. Okay? So 62 and 17, so it has to go 17, 25, 62. And that's how they have to be sorted. And then you do the same thing for all the other intermediate gaps, like 83, 95, and 28 has to become 28, 83, 95. Okay? And in this case, you do that for all the other gaps in the middle, and then you're done. And then it's now 5 sorted. Okay? And then we'll show you that one here. It's 5 sorted here. I kept the numbers from what it came before. So the 62, 17, and 25 became 17, 25, and 62. Those are the only ones we cared about. And then let's look at the blues here. 18 and 86 became, well, it stayed the same. And then the pink ones here, 7 and 16, the same. So that one didn't do too much in a lot of them. Okay? And then now we're going to do a 3 sort, which means we have to do 1 versus 4 versus 7 versus 10, and 2 versus 5, 8, and 11, etc. Okay, the red ones again here. So now it's going to be 17. Oh, it's already in order. Oh, no, it's not. 17, 47, 69, 83. Notice it's already in slightly better order. So we moved some of the big numbers up to the top, some of the small numbers to the bottom, and it's pretty well sorted. It's getting there, which means our insertion sort's going to work better. Okay, that's it now. Now we've got, we've done the 3. So the 17, the 47, and the 69 and the 83 became 17, 47, well, 69, 83, because it was 83, 69. Etc. And then now it's 3 sorted. And again, it's getting there. It's actually almost sorted at this point, which is kind of nice because our insertion sort is going to work really well. And then now we do a one more insertion sort, which is basically everybody else, which ends up with this sorting. And that's going to be nice and fast because it's already almost sorted. Okay? That's how shell sort works. Okay? Complexity of shell sort. This is an interesting one. The worst case is n squared. So if everything was reversed, it would still be n squared, no matter what your gap sizes are. Best case, though, we can get down for certain gap sizes to n log n. Although I don't think the Wikipedia page shows that. I'll show you in a sec what that's about. Average performance. Notice the question marks here. What does that mean? It means that we still haven't figured that out. Right? Still an open research question. If you go and solve this, you'll get a paper. They'll probably give you a PhD. Lots of money. I guess. I don't know. I don't know what they would do if you. But the average performance here is really, really tough to analyze. In fact, it hasn't been done yet. Right? And I'll show you that in a sec. Space complexity-wise, it is in place, which is kind of nice. But it's just an insertion sort under the covers. Lots of insertion sorts under the covers. Okay? So if you go to, let's see. Nope, nope, nope. Let's look at Wikipedia. Let's just look at shell sort. Okay. Shell sort, here it is. Okay. Shell sort has, kind of see this here. There we go. These are some of the different gap sizes that people have chosen before. Shell, in 1959, when he figured this out, a long time ago at this point, he used the following gap size, n over 2, n over 4, down to 1. In other words, do half the array, then a quarter of the array, and then all the way down to 1, and the floor function of that. And that was still n squared. Meh, not so great. Right? Still n squared. Other people have come up with better ones here. So like these guys came up with 2 times n over 4 plus 1 down to 3 and 1. I don't know exactly how I guess you'd go n minus 1 each time. But 2 to the n over 4 plus 1, and they got it down to n to the 1.5. Better than n squared, right, in the end. Right? Some other ones here, 2 to the k minus 1, just basically 1, 3, 7, all the different powers of 2 minus 1. If you use those gap sizes, you get down to order n to the 1.5, which is pretty good. Right? Lots of different ones in here. There's some squareds in here, some really wacky ones in here. Some big names have looked at this. Right? Where is it here? Knuth. One of the biggest names in computer science has come up with some of these things, right? Of course, he came up with a wacky one. Who knows? But yeah, some of these other guys like based their whole career on this, trying to figure these things out. Okay, so you can look at this. So if you are going to, I don't even know what this one's about. Unknown. Who knows? Somebody said, hey, this is a good sequence. Well, okay, you can use that sequence if you want. If you want to do this one for your homework assignment, I would pick something from this list. You can certainly come up with your own gap sequences, but if you're going to do that, give us a little bit more of an analysis, right? Like say, hey, I tried it with this gap sequence versus this gap sequence, and it performed this much better or worse or whatever. You know, that would be kind of nice. Okay, so check this out. You'll see how that goes. Okay. All right, any questions on shell sort? No? Here's the visualization for shell sort. I'll go back and I'll show you the YouTube one again. This one is one of the best visualizations you've ever seen, I think. Right? This is a bunch of Hungarian dancers. Who's seen this before? Anybody? A couple people have seen this before. Did you see it in Comp 11 or somewhere else? Yeah. The other people said they didn't see it in Comp 11. But this one's for the shell sort. It's almost a bit slow. It's like 5 minutes long to sort these things, right? But what you will see in there that they're going to sort by gap sizes of like 5, 3. I think they do 5, 3, and 1. So like the 3 and then like the 2 have to check against each other and then swap, because it's an insertion sort, right? And then the 6 and the 2, well, now the 3 check, and then the 3. I think it's that's what it is. But I'll play a couple minutes of this. And you get fun music too. Oh, no, there wasn't no other one. Best part is these Hungarians had to learn this. Like they had to learn, these dancers are like, what are we doing today? You're learning sorts. They also do quick sort and a whole bunch of other sorts. Bubble sort. This is probably some master's project, who knows? Interdisciplinary. Now a gap size of 3. Nope, no need to swap. It's also kind of a fun dance. Now you have to do a gap size of 1. I want to know how many times they practiced this before getting it right. It had to be a couple times. See how fast the insertion sort went once they were off? All right, guys, you're sorted. Yeah, well. There you go. There you go. So that's that one. Let's go back quickly and watch the other one. There's lots of them on here. Insert with Romanian folk dance. Yeah, lots of different ones you got. Lots of different ones if you want to check. Oh, we're not going to watch that. Let's see. Where was the other one? It was. Nope. There it is. There it is. Let's just quickly check on shell sort again, which was. Here it is. Okay. Okay. I think it's right there. Oh, loud. See the gaps? You can totally see the gaps now. And one more. Bing, there you go. Okay, so that's shell sort. If you have any other questions about that, let me know. All right, quickly on homework 5. Here's the deal with homework 5. You have to write 3 sorting algorithms. Okay? They are all over the internet. Okay? I am not naive enough to think that you couldn't go and like find one and like plug it into your thing. Please don't do that. Okay? I will allow you to use algorithms as much as you want. Like you can use the algorithm in sort of pseudocode and turn it into C++ for some of these. Some are going to be very easy to do. And you get a choice, though. You don't get a choice in the first one. You have to do a selection sort. It can take you probably 5 minutes to write. Okay, it's not a very long sort. Selection sort is an easy one. Okay, the other 2, you get a choice. You can choose from the following list: shell sort, merge sort, quick sort, insertion sort. If you really are like pressed for time, you could probably choose insertion sort because it's so easy. But the other ones are more fun. Okay, insertion sort is boring. The other ones are more fun. We're not going to take off more points if you don't do that, but I'll be impressed if you choose another one. Lots of people have chosen quick sort in the past because it's a good one to try to practice on. It's tricky, but it's a good one to try to practice on. Merge sort is another one that's somewhat tricky. Merge sort is a recursive algorithm in general. We'll talk about this on Wednesday. Some people have tried to do it I'm sorry, it's recursive, but it's also not in place. Like in other words, you have to keep creating more and more arrays. There are some people who've tried to do merge sort with in place. It's very tricky. It's also very tricky to get it to be fast that way. But you're welcome to try that. Okay, and we'll talk about these in the next couple of days. You can't do bubble sort. The president says so. You can't do heap sort because you're kind of doing that tonight. The third one, you can also choose another one from the list. Okay? Or you can implement any other algorithm except bubble sort or heap sort or whatever, as long as it's not something wacky. Like Bago Sort, you're not going to get any points for Bago Sort. Right? It's got to be able to finish. Right? There's some other interesting ones like sleep sort, which is very interesting too, very weird and wacky. But you can't do some of those weird ones. But that's that. Okay? This is due next Wednesday, so it's a relatively short time. I was going to make it due Sunday, but I decided, well, give you a few extra days on that. But start it now. You already know how to do selection sort, so you could probably knock that out tonight. Okay? And then the other ones will take a little bit more time, but you should be able to do that.